So, all right, in the old days, like when MSBlaster hit, you would just see the MSBlast process running in Task Manager, and you could just open Task Manager and terminate it. And that was pretty primitive by modern standards, but that's how malware worked at that time. And so now there are more covert ways to do it, so it's not as easy to catch. So they have launchers, just to launch your activity. And the point of this is to sneak another piece of malware onto your machine and conceal this from the user and perhaps from antivirus also. So typically what they does is, this is what some of the stuff I wrote, and I did a whole series of things, Python versus Wharton, trying various Python forms of malware to sneak past Wharton, and it was very easy. And one simple technique is this one. You just take the executable binary and store it as data in a data section, a resource section, and then the antivirus scanner and everything else does not interpret it as executable code, but as data, and therefore doesn't care that it's a virus. Then you load it into RAM and run it without ever storing it as an executable file, and you'll typically get away with that. Now, this is sort of like, putting a sheep mask on a wolf walking past the guard. You can encrypt or compress it as well, and you'll use APIs like find resource, load resource, size of resource to find the resource section and take the data out of the resource. This is what the API calls will look like that does it. And then you might see privilege escalation also, because you usually want to escalate to administrator to do really nasty things on Windows. So the most common way you get the malware to run, you're not actually going to save it on the file as an exe file and run it from there because you'd get caught. So you have to have some other way of adding this running process to the running list. So you typically do it by injecting it. DIL injection is the most common, easiest technique. Direct injection is more difficult, but also done. And these are ways to add code to a running process. And this is the thing about Windows. Windows is designed to make it easy for code reuse. So you can write something like a cryptographic or an image processing library, and you can sell it to a whole bunch of developers that will all use the same library. And it can load libraries dynamically at runtime to make it more convenient, so that when you launch a program, it will notice that some other program has already launched the library I need, so I don't need to make another copy. I'll just connect to that library that's already there. And you can even have it load libraries dynamically in response to user activity. And Microsoft Office does this a lot. You click on a certain function and say, oh, I need to add more software, I had to do that function. These are all ways to make programs more effective, smaller, load faster, make more money for the developers because they can sell it in more context, but it does have security consequences. And it means that when you launch an app, you can add more code to the running app, and it might be malicious, and that's a problem. So it's like most of the Windows exploits, it's a desirable feature that introduces an opportunity for bad guys. So you'll see things like virtual Alec to allocate space and memory and write process memory. And if you're taking an exploit development class, we're also using virtual Alec to defeat non-executable sections, data execution prevention, because you use virtual Alec, an API call, to allocate a new section of memory without that protection, or to change the permissions on an existing section. It's one of the API calls used for that, to turn off data execution prevention. So DIL injection is the main way to do it. This is easy. This is what we did to the Iranians with Stuxnet. You just have a library and you add it to a file. So you just run load library, and then it will load this library and add it in. Now you can either then export functions from the library and call them in the normal way. What people usually do is just put the malware in DIL main, because as soon as you load a library, it automatically runs DIL main, and you don't really plan on offering functions and using them for any productive purpose. You just want to run your malware once, so you just stick it in DIL main. That's like the old auto-run USB sticks. Until Windows XP Service Pack 1 or 3, you could just plug in a USB stick and it would automatically run setup.exe from the USB stick, and that was intended to make it easy to have USB stick programs. And of course it was real handy for malware too, and so they had to turn it off in one of the service packs. So if you want internet access to download more code, like you're running some program and then it decides, oh, I better check to see if there's an update or something, then you can inject malicious code in the Internet Explorer process. Now here, if you're trying to connect to the internet, but the Windows firewall is application sensitive. So if you try a program and it tries to connect to the internet, it'll say, this program is requesting internet access, is that okay? And it might not be okay. So instead of popping up a box that will warn the user, you just go inject the code in the Internet Explorer process that's already running, and that program already has the ability to connect, so that's another way to sneak out. You can also inject code into a higher privilege application, that's token theft, and that's you use it in a Metasploit attacks. It's a good trick. So malware has the same privileges as the code it's injected into. So if I'm in my launcher here and I inject this into AI Explorer, it'll have those privileges. So In particular, here it's just getting internet access, but it can get other privileges as well, like administrative rights, by injecting into a process that has those rights. That's why this dynamic libraries, which is what that stands for, dynamic linked libraries, is a pretty dangerous, unsanitary activity and leads to these problems. But it also leads to a lot of benefits for software developers and makes your programs run faster and smaller and everything. So like everything, it's not just stupid on Microsoft's part to make it run this way. They're doing it for a reason, and it does have a security cost. It's not like it's just a bug they can patch. It's a feature that has some value, which also causes problems. So here's some pseudocode for DIL injection. So you have a victim process, and then you get the module handle and get the process address and create a remote thread in that process. You can create a thread in another process, and then it will run code over there. This is kind of nuts, but this is the problem with RAM. RAM does not have owners and permissions the way hard drive files do. It really doesn't have a good way to stop you from doing this. Because if you double-clicked on the desktop to run another program, it would run. So if I have your privileges of the currently logged on user, I should be allowed to do this. It's not clear how it can tell this is evil. It's not that different than legitimate activities, and the same thing happens when they try to write laws against cybercrime. It is very hard to 100% clearly say exactly what makes an activity illegal and this other activity legal. Like Microsoft pops up a box and says we want to install Windows 10 and upgrade your Windows 7, and when you click no, they interpret it as yes and install it on there. Now, is that a crime? The answer is it's very hard to tell if that's a crime. It might be seen as sort of deceptive and cruel, but is it really malicious? Did it really harm you? Did it really do any damage? It's really tough, you know. That's why cybercrime laws are such a mess. And they pretty much punt, and they say you cannot do anything unauthorized, and it's up to the product developer to write down what you're authorized to do, and whatever they say, that becomes the law, which is kind of nuts too. But they didn't get there just by being lazy and stupid. They got there because it is actually very, very difficult to completely define what is a crime and what's acceptable activity on the internet. Anyway, so here's more of this code, opening this thing, virtual Alec, opening something, and then connecting to kernel 32, getting the address of it, and injecting stuff in the debugger view. So you can see DIL injection. You'll see it in disassembly. You'll see the name of the malicious DIL in strings and so on. And you can also just put a breakpoint in and look in the stack. You'll find it on there if they've been obfuscating the name to hide it from strings. And then there's the more difficult, but more subtle technique of direct injection, which is what you did in this class, putting malware in PuTTY, where you actually change the code of the program itself. And that, of course, means you have to custom write it for each app. It's not generic like DIL injection. And you have to be careful if you don't want to break the app. And that's why if you go to the blog where I got that project and go to the part I didn't write up, there's code caves where you actually hunt for unused parts of the app and put your code in there, which is even more subtle. And this, of course, is more work for the malware developer, but it's more subtle stuff. It's going to be harder to catch. All right, then there's process replacement, which is bloody awesome. I learned a technique here to defeat the City College administration. It occurred to me we had a teacher that wanted to teach an Internet of Things class, and the bureaucrats refused to get it approved. And I realized we could just do process replacement. We'll just run a section of 106 that is in fact a different class, tell the students, the administration will never know this happened, we could get the damn class taught. We didn't end up having to do it that way, but that's what happens here. So I want to run a process. I get some other process that's already running, and I replace the binary in RAM with different binary and let it keep going. Bloody awesome. So I take something like servicehost.exe, of which there are half a dozen or a dozen instances running, often running unimportant services that don't really matter, often running with system privileges. Very handy, just sitting there running some bizarre thing like some Active Directory thing I'm not using. So I have to find a service that is suspended. Now this happens pretty often, that the process is suspended because it's waiting for something. So while it's suspended, I can just replace the code and it won't care. And when it's done being suspended, it will run the altered code. So it looks like this. You create a suspended process and then create a process down there once it's suspended, and you can then resume it. And so you unmap the section, allocate a section, write process memory, then set thread context, and then resume the thread. So you freeze it, replace the guts, run it again, and now it's doing something else. But it was launched by the operating system during boot up or by the user in some earlier thing, so we didn't have privileges and given all these trusts, and then there was no verification that it was not altered in the process of running. because of course you have to be able to write to memory, right? You have to be able to write things to graphics memory and take input from the user and everything, so they can't make it impossible to change the contents of RAM. This is why it's not that easy to solve this. And so here's the game. This will release the memory, and this will allocate the memory again, and then you can write malware in it. And off you go, set thread contest, and resume thread, and it'll run again. All right, so I got some cahoots about that stuff. Let me start a Zoom session. So, where are the launchers? Get the code. Right. It's typically in the resource section, not in the data section. Which technique uses a suspended state? All right, that's process replacement. Good. All right. Which one requires the most customized code? Direct injection, okay. What's the most common technique? Still injection, good. And which one uses find resource? That's resource extraction. All right. So these are my winners. So then there's hook injection. This is going to be a recurring theme in this class. There are many, many ways in Windows to say, wait, before you do that, go do this. Wait, before you do that, go do this, all over the place. And of course, malware loves that. So hooks are messages. In Android, they call these intents. A signal sent to the operating system that some event has happened, and perhaps you'd like to run code driven by this event. And you can have malicious hooks, which will run when these events happen. All right, so you can load a DIL when that happens. So the user is doing things, then events happen, like they press the keyboard or the mouse or something. This goes to the OS, which sends messages, and those go to various threads and processes that are listening for the hooks. And all I do here is add a malicious DIL that is also listening for those hooks, so that when those things happen, this other code is informed. And of course, this is enormously useful, because if I want to do something like have a wireless keyboard that has some weird driver running a different process, then I want to respond to those key presses and treat them as normal key presses. So I want the events to pass to the normal application. And the same thing happens, one of the extreme examples we talked about before is Gina. If I want to log in with some different hardware, then there has to be some way for the operating system to know that and accept messages from something else. So this is a necessary way to decouple one activity from another. And so there are local hooks which look for information running in the same process. And there are remote hooks which look for information from a different process. And of course the remote hooks are sort of more obviously exploitable. And both of these are in Android too, as far as I know. So there's high-level remote hooks that require that you have an exported procedure in a DIL. And there's low-level remote hooks which require that the code I run is actually included in the same process already. They amount to about the same thing. They're both remote hooks where the actual signal came from a different process telling this process to do something. And this is a really general concept. I saw it in the Hyperledger blockchain. I was just talking about it the other talk. In a Hyperledger blockchain, the simplest case they could make for demonstration had a ticker tape that records the price of stocks, and it sent events every time a price changed, because that is so natural. You need to tell some other process what's happening, because it might want to do something like trigger a buy or sell order or alert or something. It is just very common that something happens and you want to tell other apps that this happened. So keyloggers are the obvious case. If I keylog after the key press, these events happen and I want to capture them, so I'll use these procedure types. Typically, these are the keyboard procedure types that are used to detect keyboard activities. And so you call this set window hook X is the API call to set up a hook. And you tell it the parameters, type of hook, which is one of those two from the previous slide, and then you point to the procedure and have a handle to the DIL and so on, and you can just have as many as you want. They're just like services. They're running in the computer waiting for the event that will trigger them, and you need this capability. So you can target one thread, in which case you would only get the information coming from that one thread as a source, which is probably okay for some things, but it's not okay for keylogging, where you really want to catch all the key presses regardless of which window they're aimed at. So keyloggers load into all threads, which is relatively expensive but it's a thing you have to do. Another thing you could do is target a Windows message that's rarely used. There are some Windows messages like this one for computer-based training, which is not used much, and so you could use that to mean some signal for your malware. You could hijack and overload that to send a signal of interest to you, and it probably trusts that it's not being used already. Anyway, so here what we're going to do is see the code that does this, load the malicious DIL, then get the address to malware proc, then call next hook X, and it'll send this computer-based training to a notepad window, and that will tell us notepad to load a DIL. That's what this sets up. So here it calls, finds the file name of hook.dil. Here it gets the handle to that process with get process address. Then it gets the handle to notepad, and then it sets a hook based on the CBT method, so that when my malware sends a CBT event to notepad, notepad will load that DIL. So now I can load an extra DIL into notepad, as an example. Another one is detours, which I made me laugh when I first heard of it. This is literally, before you go do something else. And this is for version changes, I think. So I can have code written for 95 that runs on 98 or something. Well, before you do that, go do something else. So this makes it easy for everyone to add. Well, you can add another section to the binary, which is a detour. Go do that. Modifies the PE structure to have a detour section, and that contains the new PE header with a new address table, so it's used instead of the original one. And so you'll see in, say, PE view, you'll see a detour section with another import name table down here. So you have extra functions there, like evil.dil, being loaded in the detour section. All right. And then there's APC injection. It's just amazing. My first introduction to this was when I taught Windows Tech Support, and one of the big issues in Windows Tech Support is my Windows machine is slow because too much junk is loading when I boot up. And I started learning techniques of finding how many things launch automatically, and the answer is a lot of things, like 60 things launch automatically, and they don't all launch from like the startup folder or anything reasonable. There's like 30 or 40 different ways to make things launch automatically. So it's actually really hard to find them all, which is kind of insane, and that's because of the way Windows is made. They just keep taking what's already there and patching on more stuff like the Frankenstein monster, and it grows and grows because they just want to be the answer for every problem and get it out fast, and the fact that it's a snarled up mess is not really as important as getting it out fast. And I must say they're #2 company in the world now. They're making record profits. This is apparently true. This is the way to make money, is to rush it out the door, have it half broken, all full of bugs. You get it out fast and make sure it has every possible feature. That's what people want. Quality is not the way to make money. Anyway, that's the American way. Ethernet is similar. There used to be something called token ring, which is really nice. You wait your turn on the network. Is it your turn to speak? It's your turn to speak. If you have something to say, I'll take your message, put it over here. So if a token ring ran at like 4 megabits per second, and it would really deliver 4 megabits per second of data, there was no waste. Then Ethernet came out, where everyone just shouts at once. Frequently, messages collide and get broken. Then we just shout again until it works. So we make this sloppy piece of junk that fails, and we put a patch routine, and this turned out to be much cheaper and faster, and wipe out token ring in the marketplace. You know, quality was not as good as just a sloppy thing that worked. That was much cheaper and much faster. So same thing with Windows. Anyway, so asynchronous procedure calls will direct a thread to execute other code. And this is what, if you do networking, even in Python, especially in C, you have to make your hood asynchronous, otherwise it will wait for something to happen, and you don't want that to happen. You want it to put it in a queue and do it when the right time comes and let other things happen while that's going on. So you wait for things, you can tell it to wait for things down here and sleep for a period of time, but only one thread will stop and other threads will keep moving. So there's kernel mode APCs and there's user mode APCs. These are making requests for some other process to run at a different time. And so you can do it from user space. This uses QUser APC. The thread has to be in an alterable state, which is like a suspended state, just one of the states of a thread. Then the most common thing you do is wait for single object. And then many threads are typically in their alterable state, which I think means they're not doing anything and they could be changed at this point. So there are parameters, handle to the thread, the function to run, a parameter for the function. So you can tell it, run this thing when you're good and ready. And so here's what you do. You call open thread to get a handle to the thread. Then you call QUser APC with the parameter to tell it what DIL to load. And then you give it the information about the data, and it launches servicehost.exe. So I've now asked servicehost to please run this later with system privileges for me. So you can, this is what crazy case. You might have a kernel mode rootkit, and now it wants to do something that you cannot do from the kernel. We're used to saying, there's things you can't do from user land and you have to get in the kernel, but there's things you can only do from user land. And the kernel can't do that either. So APCs are one way to do it. So you'd use these routines to create user land asynchronous procedure calls from the kernel. And that's what you see here, KE insert Q APC. That will insert an APC from the kernel. So that's all there is of that. So which one manipulates messages from a process to itself? Okay, that's called a local hook. It is, by the way, kind of nuts how much parts of Windows talk to themselves. And if you look at a modern Windows machine and do netstat -an pipe more, you will find that it is listening on about 20 high-numbered ports on the network socket on 127.0.0.1, so it can send network traffic back to itself. That was not true until Vista. It's true in all versions of Windows, and I've tried many times to talk to the Microsoft people I know and find out what is that junk, and I've never got a clear answer. Why would you send things to the network and back on a loop pack adapter? But that's what it does now. It's a similar thing here. It's talking to itself in a strange way. This is a more common solution for problems than you would think it would have to be. Anyway, which item hooks all processes? Okay, keyloggers, of course, have to hook every process to get all the keys. Which one adds a new section to a PE file? Does detours add a new section, just like we did when in that hacking putty project? All right, so which one lets a kernel mode rootkit run user space code? Okay, that's APC injection. And which technique only works when things are alterable? That is also APC injection. All right. It's a property of it. So, Forrest and Peter, a real name is Bloody Monday, will have to come out of the closet if they want to get points. Peter D is won twice. Forrest wins once. And Bloody Monday. Aha, a chat message. Perhaps it is the identity of Bloody Monday. It is. Okay, good. A likely suspect. Okay, good. Thank you. All right. So let me just see if there's anything I have to say about the project. We have 13 and 14 due this week. Then next week, nothing due. Week after that, 15 due. So let me just take a quick look and see. Yep, it's IDA Pro and kernel debugging. We talked about that, and SSD dehooking. We've already talked about these in previous times. There's nothing too new and exciting coming up here. Windows 2.16, that's right, you need it to do compiling C and C constructs, which again are things we had in earlier classes. The correlation of projects to chapters is not too perfect this year, but anyway, there they are. And there's a lot of extra credits, and people have been turning them in. Where are they? Oh, maybe they're not in this class. I think I got them integrated with the original project in this class. Anyway.
So careful with the kernel debugging. I've killed my virtual machines.
You killed your virtual machine with the kernel debug?
Yeah, but then I like reloaded and everything.
Oh, well, that's,
yeah.
I'm surprised. I didn't know you could, because you're not changing anything.
Well, I was just playing around.
Okay, yeah, fair enough. Because LiveKD does not let you change the kernel, so I wouldn't think you could kill your machine.
Yeah, so I was just playing with it, and then I just reloaded it.
You just had to restart it, or you had to reload it?
No, I had to reload the image.
Oh, that's interesting. I'd be interested to know what you did, because
I'll try to replicate it.
I didn't think, remember what I did? I'd like to know, because I didn't think it was harmful.
Yeah.
But of course, we are working with malware, so you're working in a virtual machine. Of course, it could be harmful. I wouldn't be surprised if some of those goofy things, like there's something I had that hooks the table that you downloaded from somebody, and that could very well, and you're running a really old version of that stupid firewall zone alarm, and I wouldn't be surprised if that stuff is pretty harmful.
Yeah, so, yeah.
Yeah, it might, because that stuff was written for earlier versions of Windows and stuff, it might very well do something, especially that one that's just like demonstrate a hook written by some amateur. That might well do something it shouldn't do. It's like malware. You might well not be putting something on it you can't really get off.
That's why you do it on virtual machines.
That's right, yeah. I remember there was a CTF I did one time, and they give you a program, you download it and run it, and it destroys your machine. And they're like, how stupid are you? I said, well, I didn't expect that. God damn it, you broke my Kali machine. I guess you could say I was supposed to be thinking about that, but I really wasn't thinking about that in the CTF. I feel kind of abused, but at least I didn't run it on my host. But that's rude. Anyway, all right. Well, I guess that's it. I'm going to go to the lab and help anybody who wants to work there. That's enough of this. So we'll be back next week for a guest.